we need to show that 1/3 of the surface integral of the dot product of r vector and dA vector is equal to V, where V is the volume enclosed by the surface S. Now because of this dot product, we are going to use the Gauss's divergence theorem. And of course, there is a surface integral over here. So before starting with the proof, let's recall few points. These are very important remarks on divergence, curl and gradient. First one is, the surface integral of the dot product of n vector with f vector is equal to the volume integral of the divergence of this f vector. Then is the surface integral of cross product of n vector with f vector is equal to the volume integral of the curl of this f vector. Then is the surface integral of product of n vector with phi is equal to the volume integral of the gradient of this phi, right? And this first result is nothing but your Gauss's divergence theorem. This is a result for the Gauss's divergence theorem. And now we are going to write the integral expressions for gradient phi, divergence of f vector and curl of f vector. That are also known as the definitions for the differential operators. First one is gradient of phi, that is the grad phi. So just write limit v tends to 0 on the surface integral of n vector its product with phi ds divided by v. Then is the divergence of f vector, that is limit v tends to 0 surface integral on, because it is a divergence, so we write the dot product of n vector with f vector divided by v. Similarly, for the curl of f vector, we write limit v tends to 0 the surface integral on the cross product of n vector with f vector ds divided by v. Right? Let me also introduce the Gauss's divergence theorem. The surface integral of f vector, its dot product with n vector, ds is equal to the volume integral of the divergence of f vector dv. So we are going to use this result in the proof. Alright, let's start with the proof. We need to show that 1/3 of the surface integral of dot product of r vector with dA vector is equal to V. That is the volume enclosed by the surface S. So for this, let this r vector is equal to xi vector plus yj vector plus zk vector, right? Okay, what is dA vector over here? dA vector is the vector area of the subsurface and ds is the magnitude of the area of the subsurface. If I multiply n vector with ds, then I get dA vector, that is the vector area of the subsurface, where this n vector is unit vector along the normal to the subsurface, right? Okay, now to prove this result, I need to use the Gauss's divergence theorem over here. What Gauss's divergence theorem result is? It is the surface integral of dot product of f vector with n vector ds is equal to the volume integral of divergence of f vector. Now here we are having dot product of r vector with dA vector, right? And here I am having n vector into ds. And we know that n vector ds is dA vector, that is the vector area, right? And for f vector, we are going to use the r vector, right? Okay, so let's write the left hand side of the result first. That is 1/3 of the surface integral of dot product of r vector with dA vector, applying the Gauss's divergence result over here. So this is volume integral of divergence of, for f vector we write r vector. So this is equal to the volume integral of divergence of r vector, that is the del dot r vector dv. That is equal to the volume integral of, okay, writing del as curly over curly x I vector plus curly over curly y j vector plus curly over curly z k vector, and its dot product with r vector, that is xi vector plus yj vector plus zk vector. When you take the dot product of these, you get 1/3 of the volume integral curly by curly x of x plus curly by curly y of y plus curly by curly z of z dv. So this is equal to 1/3 of the volume integral. Okay, curly by curly x of x is 1 plus curly by curly y of y is also 1 plus curly by curly z of z is also 1 dv. This is 3. So writing this as 3 dv. Taking this 3 outside, we get this to be as volume integral of dv, that is equal to v. Hence we have proved that 1/3 of the surface integral of r vector with dA vector is equal to the volume V that is enclosed by the surface S. Alright, thank you.